Welcome to lecture 12. So in this lecture, we will discuss protocols for resource sharing among tasks. So recall that in chapter 11, we had gone through all the basic definitions of what is priority inversion, what is unbounded priority inversion. So the basic priority inheritance protocol, so for this you'll have to go a few more lectures back, where we had discussed the idea of priority inheritance. So the main idea behind this scheme was that since a task in a critical section cannot be preempted, even though it's a low priority task, it should be allowed to complete as early as possible such that it relinquishes its resource, right? Because it is possible that high priority tasks may be having unbounded priority inversion. They could be having simple priority inversions. Hence, it's a good idea to ensure that if, let's say, a task is holding to a preemptible resource and nothing can be done, it should at least complete as soon as possible. How do we do that? We can raise its priority so that other low priority tasks will not be able to preempt it. So, the important thing that you need to understand is that, let's say, this task in consideration, TL, is holding on to the CPU because that is needed and it's holding on to the resource. If it gets preempted from the CPU, it cannot finish its work with the resource. So that is why it needs to hold on to the CPU as well, which means its priority has to be raised. This will stop all problems of both simple as well as unbounded priority inversion. The question is we raise it, but raise it by how much? We should ideally make its priority as high as the task it is blocking. So if let's say its priority is X and the task that is blocking its priority is Y and Y is clearly greater than X, where a greater number indicates a higher priority, then ideally the priority of X should be raised to Y such that it will be able to execute or get the same level of fairness as far as the CPU is concerned that Y would have gotten such that it can finish its work. So the priority inheritance protocol mainly kicks in when a resource is busy. So what happens is that requests to lock the resource are queued in FIFO order. And whenever a higher priority task TH blocks, and why would it block? Because the lower priority task TL is hanging on to the resource and also taking CPU time, as I have just mentioned. So at this point of time, a priority inheritance protocol will kick in. So what will happen is that the inheritance clause of this protocol will kick in, where the priority of the task that is there in the critical section, which basically means the task that is working on the resource or using the resource, its priority is raised to be equal to that of the higher priority task in the queue. Which queue? It is the FIFO queue that has all the tasks. Okay. So basically, the point is that if we look at all the tasks and we have a first in, first out FIFO queue, and we look at the priority of every single task, then the point is that we raise the priority of the task that currently has the resource to the maximum priority within this queue, such that, as we have discussed in line with our philosophy, the task, of course, completes sooner, completes earlier, but along with that, it does not get an undue advantage over other tasks, which again have a higher priority but are not waiting for that resource. So that is basically the broad idea. And as soon as the task releases the resource, it will revert back to its original priority value, right? So its priority will kind of increase like this, it will increase like this, and then it will come back. So of course, if it could hold multiple resources, if it's holding multiple resources, then of course the priority would be determined by the other resource that it is holding, right? So the other resource would have another FIFO queue, and we'll have to take a look at the priorities of those processes in the FIFO queue of that other resource. But pretty much as far as this resource is concerned, the temporary increase in the priority will be rescinded. And as I said, in case it's holding other critical resources, let's say it's holding another resource R2, we look at the FIFO queue of R2, find the one with the max priority, and then raise the level to the max priority. So let us now look at the traditional resource locking operation. So we are currently seeing a kernel mode implementation. So what we do in the kernel is that, given the fact that this is a sensitive operation, we don't want any interrupts in the middle. Otherwise, our data structures will get corrupted. So of course, if the resource is free, which means its counter is greater than 0, then we decrement the counter and pretty much we get the resource. Otherwise, if let's say it is 0, which means that the resource is busy, something needs to be done. So what needs to be done? Well, we have to do a context switch. So we do that. And then in the kernel code, the state of the task is set to blocked. So the task basically blocks. And then we insert the current task in the queue that is associated with the resource. So this is a standard scheduler loop. Once the task is inserted into the queue, we just find the next task to schedule, load its context, and execute it. So let us now look at the basic locking protocol with priority inheritance. So the entire structure is the same. We start with disabling the interrupt. Then we see the lock is free or not. So the reason we have a counter is basically because there could be multiple copies of the resource. So when we acquire a copy, we just decrement the counter by 1. So in general, in any resource or the software lock that protects it, it will only vary between 0 and 1, mainly because it will be a single copy. Nonetheless, what you see is a generic mechanism where we decrement the value of the counter. We set the holder of the resource to the current task. And furthermore, in the semaphore list or in the lock list, resource list, whatever you may call, we add the value or the pointer to the resource into the list. But this case is not as interesting as the other case, which is that when we actually find that the resource is currently being used. So in that case, well, the first few lines are boilerplate code in the sense we save the context. We have to block the current task. There is no other option. So we set the current task state to blocked. And we insert the current task into the queue associated with the lock. So basically, every resource has a software lock that protects it. And that has a queue. So this queue we are arranging as a priority queue. Nonetheless, it's a queue. So we insert this task into the queue and it is sorted according to max priority. So this is the key step. This is the crucial step where we actually do the priority inheritance. Prior to this, we don't do the priority inheritance, but we do it after it. So the key idea here is basically that we look at the highest priority task, the priority. So we find the priority of the task which has the highest priority, and that is set to the priority of the current to the lock holder, right, the resource holder. And then, of course, we call the scheduler. The scheduler selects which task needs to be executed next, and we load the context. So the unlock operation, if I were to look just at the traditional implementation, this is what it would look like. Again, we do the same things. We disable interrupts and we enable interrupts at the end. This is basically to ensure that this piece of code executes atomically. So here again, we look at essentially the resource and we look at its queue. If its queue is empty, which means if no task is waiting, then we simply increment the counter, which pretty much releases the lock, and then we move forward. However, if the queue is non-empty, it's not empty, which means another task is waiting, then what we do is that given the fact that it's a priority queue, we find the task with the highest priority. All right. So this task is called next to run. We set its state to ready and we insert the task next to run into the ready queue, which means it's in the ready queue, it needs to be executed next. And then of course we save its context, right? Save the context of the current task. We do the scheduling and we load the context of this task which is next to run. So this is a very traditional implementation of a scheduler in an operating system. In the case of priority inheritance, it is precisely this schedule block which gets changed. So here again we do the same thing by and large. We disable interrupts, we enable interrupt. Okay, and given the fact that this is also not important, if which is if the queue is empty. So if the queue is empty, we simply increment the counter. Hence, these lines are not important. Given that they are not important for the current discussion, because we are mainly looking at the fun part, let's look at the rest. So what happens is that the priority of the currently executing task that is releasing the resource, its priority is reset to its original or previous priority. So basically whatever was a priority before acquiring this resource, its priority is reset. Furthermore, what we do is that we again take a look at the queue which is not empty. So in the not empty case, we come to this area. So again, we get the first task in the queue which is sorted according to task priority. So we get the first task. So this one has the largest priority. It's next to run. We set its state to ready. We had done this previously as well. And we make next to run the holder of the resource such that it can run. All right. And furthermore, what we do is that we add next to run to the we add SCB into the semaphore list of next to run. We insert next to run in the ready queue and then we execute it. So this part is again quite standard, but what is actually different in the case of an unlock, which was actually not there in the traditional version, is basically this, which is that the priority is reset to the previous priority or the priority that existed prior to acquiring the resource, right? So I'm using acquiring the resource and acquiring the lock kind of interchangeably because every resource is actually protected by a software level lock. So then the pseudocode is very simple. If the resource is free, then grant it. If the required resource is being held by higher priority task, well, then you have no choice. Wait for the resource. If the required resource is being held by a lower priority task, then of course, then the angle of a choice comes in. So then we wait for the resource, right? But we raise the priority of the low priority task that is holding the resource to the priority of the highest task that is waiting. So this is the idea of the priority inheritance protocol. So the key point is that it does, in a sense, prevent unbounded priority inversions because the point is that its level is raised, right? Its level is raised. So the moment you raise priorities, so raising priorities pretty much reduces priority inversion because the moment you raise the priority of whoever is holding the lock, then the point is that it will finish and it will finish as soon as possible. And so basically, if it finishes as soon as possible, then the highest priority task will get the resource. But if let's say the low priority task, which is holding the resource, if that is not allowed to execute, then only you will have unbounded priority inversions, because this is where intermediate tasks which are not interested in the resource will continue to execute. So they will pretty much have fun. So the point is that we may be doing it too much, in the sense that we may be swinging the pendulum too much to the other side. So intermediate priority tasks, in this case, by raising the priority of TL, let's say, which is holding the resource to a much higher value, we are pretty much cutting out intermediate priority tasks, right? So they cannot preempt it. But the fact is that they are also being delayed. And they are being delayed. Why? Because a lower priority task, it's temporarily, its priority is being jacked up. So this is known as inheritance blocking. So as we see, we cannot be uniformly fair, right? So if we are being fair to a high priority task, we are being less fair to intermediate priority tasks. That is inheritance blocking. And if we are being fair to intermediate priority tasks, then we'll not be fair to the high priority task, and that would be unbounded priority inversion. So pretty much unbounded priority inversion. There is a trade-off between unbounded, let me call PI as priority inversion. So there is pretty much a trade-off between them and inheritance blocking. So the idea is that I can have a lot of inheritance blocking, so I can reduce my unbounded priority inversion to zero. But that again will not be a good idea, because again threads will suffer. So balance is needed. The working of PIP, as you can see, if I were to draw a small diagram, so I have task Ti, which has acquired a resource, its priority is 5, other task priority is 10. So initially what happens is that the low priority, so in this case, higher this number, higher the priority. So Ti is holding a resource, but Tj has the higher priority, green color. So the higher priority is transferred to Ti, in the sense it inherits the priority, and now Tj waits for Ti to complete. So this is an example of a priority inversion, no doubt. But the fact is that we are cutting out this unbounded priority inversion problem. All right, so ultimately what will happen is that after Ti has finished its execution, then Tj will get access to the resource because it had a higher priority and will start executing. So what are the shortcomings of the basic priority inheritance scheme? So it has two shortcomings primarily. So we will see that there is a phenomenon called chain blocking, which is explained later. And furthermore, we could have deadlocks, in the sense that we could have a cyclic dependency of resources, right? And we will see what is chain blocking. Okay, so we'll see that one or two slides later. So these are the two primary problems with PIP, which are lack of deadlock prevention and susceptibility to chain blocking. So let's first look at deadlocks, then we will look at chain blocking. So consider two tasks T1 and T2, which are accessing the critical resources CR1 and CR2. So assume that T1 has a higher priority than T2, but T2 just starts running first. So what can happen is T2 can lock a resource, T1 can lock a resource. But the point is that T1 may want to lock a resource, that is. So it is possible. So here is what can happen, that T2 starts first. It has a lower priority. It locks resource R2. Then T1 comes, so then it preempts T2. It locks resource R1. And then it tries to lock R2, but this is where there is a conflict because T2 is already blocking it. And then T2 starts executing, but then it tries to start to lock R1. And since R1 is non-preemptible and already T1 holds it, we see a classic deadlock situation between T1 and T2. So of course, the priority inheritance protocol does not do anything to prevent it. So what essentially happens is, given the fact that, in this case, T2 would pretty much inherit T1's priority, it will come and pretty much stop over here. So this was one problem. which was deadlocks. But now let us look at chain blocking. So let us assume a task that needs to use a set of resources, right? Not just a single resource, but a bunch of resources. So every time it needs a resource, if it undergoes priority inversion, this will be called chain blocking. So let's see an example of chain blocking. So assume a high priority task T1 that needs several resources. So the example would be like this, that T1 is a high priority task which needs several resources, and T2 is the task that is executing. All right. So T1 in this case is waiting for resource 1. So this means that T2 will inherit T1's priority. So it will execute at a higher priority. Then what will happen is that T2's priority will again revert back, and T1 will again execute at its natural priority, which is a high priority, and will get access to resource 1. Now assume that it needs access to resource 2. Well, again the same thing will happen. Again it will wait for T2. T2 will finish using resource 2, and then it will give it to T1, as you can see over here. So which basically means that task T1 had to wait twice. It had to wait once for resource 1. It had to wait a second time for resource 2. So an example of chain blocking would be something like this. So assume we have task T1 which has the highest priority. So it will do some local work. It will request for R2. So at that point, task T2 would have acquired R2. So it will work with R2 and then it will release R2. So green means release. Then T1 will get R2. Again, it will do something, again request R3. Task T3 may be accessing R3s. After some time, it will release, no problem. Then it will request for R4. So as you can see, every time it requests for a resource, if it needs, n resources, n times it has to wait. So it will suffer n priority inversions, and this is known as chain blocking, which basically means that you request for a new resource and then you may be blocked for a long time, which is not something that is in the best of our interests, because after all, T1 is a high priority task. It can maybe wait a little bit owing to the fact that the resources are not preemptible. But let's say if it needs 10 resources and it is getting blocked 10 times, that is not fair. So as we have seen, the main problems with PIP are this chain blocking and deadlocks. It does solve many issues in the sense it does take care of the issue of unbounded priority inversion. In the sense, if you are at a low priority level, you get jacked up to a high priority level, right? And this priority level is greater than equal to the priorities of all the tasks that are waiting. So this ensures that at least it has the highest priority among waiting tasks. So of course here we are assuming a first in first out kind of scheduling, in the sense FIFO. If two tasks are the same priority, the one that came earlier uh, gets the precedence. So given the fact that TL was executing, it was there in the first place. So then it will of course continue even if there are others in this list which have the same task. So it will execute and it will come back. So the issue of unbounded priority inversion is something that PIP solves very well at the cost of introducing two more problems. So this is again an illustration of chain blocking where all the low priority tasks grab the resources. Then the high priority task T1 tries to acquire the resources one after the other, R2, then R3, then R4. And what we can see over here is that R2, well, it waits for it till T2 finishes, then it acquires it. So it acquires, slowly one resource after the other, suffering priority inversions and delays, which is known as chain blocking. And because of this, it may miss its deadline also. So let us now look at some properties of PIP And of course, we will design two more protocols to improve PIP, right? Rectify the issues. But let's at least take a look at their properties via two theorems. So theorem one, assume a task TA can be blocked by k low priority tasks T1 to Tk, primarily due to the cases that we have seen due to the usage of resources. So now the issue is, for how long can TA actually be blocked, right? So we are talking in this case of a single resource, right? Not multiple resources, but a single resource. So in this case, the idea is that if you think about it, some lower priority task could be executing and TA comes. So let's say it comes at the worst possible moment. It will have to wait for the low priority task to finish. Given the fact that there are no unbounded priority inversions, the low priority task will continue to execute unless it is preempted by a task whose priority is higher than TA. But then, of course, we have no reason to complain. Otherwise, it will continue to execute, it will finish, and then at that point of time, if TA has the highest priority, it will get access to the resource. So the question is, what is this duration for which TA is blocked when there are no tasks in the system who have a higher priority than TA? So this is basically, the thing is that any of the k low priority tasks could be inverting the priority of TA. So this value over here, if we consider the worst case, will be the maximum execution time across all the low priority tasks, right? So if let's say I take I to be an iterator, where I is, let's say, element of the set 1 to k, right? So if I is of in this range 1 to k, and if we consider the fact that mm, among these k values, uh, and I'll take the maximum, that is essentially the largest duration for which an inversion on TA can happen. The main reason being that the inversion on TA cannot happen twice. The reason it cannot happen twice is because when the low priority task finishes, whatever it is, at this point of time, TA will have the highest priority given our assumptions, and TA will execute. So nobody else can execute. So that's the reason. So the key insight for this theorem is that, again, if we are only considering low priority tasks, that being the assumption, so keeping our assumption, TA cannot be blocked twice. That's the key. That's the crux. Okay, so it cannot be blocked twice. So we can slightly extend this argument. Let us say it needs k critical resources, right? So then the maximum duration for which it can be blocked, where again we don't consider tasks with a priority higher than TA, is nothing but the summation of max EI, right? Where EI is basically the set of all the tasks which are interested in a given resource. So what we do is that, let's say if there are k resources, we number them 1 to k. So let's use a different iterator here. Let us use J, which is basically referring to the resource number, and let max EJ be essentially the longest execution time for a task whose priority is less than TA, which is interested in that particular resource, right? In resource J. If we just add them up for every single resource, this will give you the blocking time for task TA, right? Under PIP, under the priority inheritance protocol, this will give you the blocking time. And of course, the key insight is something that we have discussed here, that a task cannot be blocked twice, right? So for any given resource, it can't be blocked twice. It's blocked once. The next time it will get it, and if there are k resources, it will get blocked a maximum of k times, and each time the duration is upper bounded by the duration of the largest execution time of a low priority task for that resource, right? For that critical section. So that is why so for the first reason the max comes, for the second reason the summation comes. So this is the final expression for the blocking time when there are k critical resources. But mind you, our assumptions are important. So it is important to take a look at this video, take a look at, let's say, this slide once again, and look at all the assumptions we have made. And the key assumption is that there is no task with a priority that is higher than T. Otherwise, it will execute and then we have no reason to complain. So the key point is that I can get delayed once because the resource itself is non-preemptible, but I cannot get delayed twice. Right? Delayed in a sense, delayed with priority inversion. Right? So keep these assumptions in mind. That will help you understand both theorem 1 and theorem 2 quite easily. So there are 4 practice questions. I will quickly skip these slides, but as you can see, to solve these practice questions, as you can see the lion chasing the deer, you need to have a very similar level of motivation, but I will quickly skip these questions. So these are easy questions to answer. Nonetheless, uh, I'll, okay, let me do one thing. I'll maybe just move slightly slower such that you have enough time to at least take a look at this question and take a screenshot. So I will again hang on here for 3 seconds. All right. So now let us discuss a protocol that fixes some issues of PIP. So this is known as the highest locker protocol, or HLP. So what happens is that, of course, here again the assumptions are important. So we assume that during the design of a system, for every resource we know all the tasks that are going to request for it. So we know all the tasks and we know their priorities as well. So this is why these static priority algorithms work really well, because the priority is assigned to a task. It's kind of tied to a task and it never changes. So the key point is, given a resource S, we know all the tasks that will possibly request for it. So then the ceiling, where of course we are assuming a FIFO order, the ceiling is basically the maximum priority of all the tasks which will request for a given resource. And the ceiling is resource specific. So the ceiling is tied to the resource. So the ceiling priority of a resource is equal to the highest priority of all the tasks that are expected to use that resource. They may not use it in every run, but they are at least expected to use it sometime in some run. And this is known a priori. So now the key, so here is the key, it's just a one line protocol. When a task acquires a resource, its priority value is raised to the ceiling priority of that resource. Okay, as simple as that. That whenever any task acquires a resource, we just bump its priority to whatever is the ceiling priority of that resource, which is the maximum priority of all tasks that may ever possibly request for the resource. So this may appear simple, it's quite profound and quite powerful, in the sense that it helps us address many of the shortcomings of PIP. However, it introduces new complications, which of course we will correct in a later protocol known as the priority ceiling protocol, right? So this will kind of rectify things in PIP and HLP. But let's understand HLP first. So during the design of a system, a priority value is assigned to all a ceiling priority value is assigned to all critical resources, because we know our tasks and we know our priorities. So when a task acquires a resource, we have already discussed, its priority is bumped to the ceiling priority of that resource, and then its priority is restored to its previous value, as we have seen in the case of PIP. So of course the ceiling are when you are looking at FIFO scheduling, right? So is basically the maximum priority of these. If of course we are doing round robin or something, where there is no natural ordering between the tasks, then it may be necessary. It is necessary. I'm sorry, to increase this by one, assuming that higher priorities mean higher numbers mean higher priorities. Otherwise, we subtract one. But anyway, let's proceed with the discussion that we are going with a first in, first out order. That helps keeps things simple. So, of course, the correlation between the priority and the number. In some examples, lower the number, higher the priority. In some cases, higher the number, higher the priority. But for the specific example, I will explain. For example, in this particular setting, lower the number, higher the priority. So we have three tasks, two with priorities 2, 5, and 8, and the highest is 2. So of course, different operating systems, be it Windows or be it Unix, they assign, they have different kinds of protocols. So some of them may say that higher the number, higher the priority. That's what Windows would do. Unix, on the other hand, Unix, Linux would say lower the number, lower the priority. So it doesn't matter. We can, our the definition and the workings of the protocol don't really depend upon which convention we choose, as long as this is made clear. So the key point is that as soon as a task acquires a resource R, its priority is raised to the ceiling of R. Right? So this is the only thing we care. Internally, whether it's max or min, those are not important problems. So this helps eliminate several problems. It helps eliminate the problems of, as we have seen here, also there is no unbounded priority inversion. The reason is quite similar to PIP, right? So I will not go through it once again. Furthermore, it stops deadlocks. So we will see why. So this will be apparent in the next few slides, where we will essentially show that look, prior to acquiring a single resource, the rest of the resources have to be free. And this is why a cyclic dependency will not occur and a deadlock will not happen. But this issue is going to be discussed. Now, coming to chain blocking, again, the reason is the same, that prior to acquiring the first resource, the rest of the resources have to be free. So, the reason is the same, and we'll introduce a theorem which will basically prove both, right? Both the deadlock freedom as well as the freedom from chain blocking. So, we will discuss both. So, the only real problem with the HLP protocol, which is why it is not used in practical settings to that extent, is that it introduces inheritance blocking, which is something that we have seen in PIP also. So the idea here is that again we boost the priority of a process, right? Of a task. So in PIP, basically the way that the priority was being boosted was we were taking a look at all the tasks that are currently waiting on a resource, right? And among them, we were finding the one with the highest priority and then boosting the priority of the resource holder to that. That was still fine, but let's say assume in this case there is some task which may acquire the resource or may not, depending upon runtime values, right? And its priority is very high, let's say 1000. Then this protocol will simply jack up the priority of the resource holder to 1000, which will which will allow it to monopolize the CPU, and all other tasks which have nothing to do with the resource, they will all get blocked. And here again, since we look at a theoretical possibility of a task acquiring a resource, this is overly conservative, which leads to a lot of inheritance blocking, because it can be argued that many a time the priority of the resource holder is unduly high, right? Is unacceptably high. So that being the problem, let's look at a few. graphical illustrations of this. So here again, lower the number, higher the priority. So assume T1, which has a like a middle priority between T2 and T3, that has acquired the resource. So the moment it acquires the resource, regardless of whoever is waiting for it, its priority is bumped to 2, because 2 is the ceiling value. 2 is the largest priority among all the tasks. So its priority is raised to 2. After that, if T2 wants to acquire the resource, then it kind of falls behind in first come first serve order. And also, well, that's not that important. The fact is that T1 is holding on to the resource. So basically, T2 waits for T1, and in this case, T1 actually executes given our FIFO order of execution. And other tasks which actually had, technically speaking, a higher priority than T1, higher base priority, that is, because 3 and 4 are higher. In this case, smaller the number, higher the priority. They get blocked out. So these tasks are the one which suffer from inheritance blocking. All right. So they get blocked out. They are the ones that suffer from inheritance blocking, because even though they are not interested in the resource, but still T1 is running with priority 2, with the number 2, which is the highest priority at the moment in the system. So the highest locker protocol is used for resource sharing, and the key point or the key corollary that we are talking about, the key theorem, I'm sorry, which prevents both chain blocking as well as it prevents deadlocks, as well as it gives it some interesting execution properties at the cost of inheritance blocking, is that once the task gets any one of the resources required by it, right, once it acquires its first resource, it is not blocked any further. So again, this blocked word, this is contingent on our assumptions. So basically, I would like to elaborate on this. So assume that I have a task Ti which wants multiple resources, R1, R2, R3, and so on. So the moment it acquires R1, its priority becomes equal to ceiling of R1, which can be greater than equal to the priority of Ti, right? So the question is that what can we say about R2 and R3 at this point of time? So if R2 is so let's consider the simple case that both R2 and R3 are free. Then there is no problem. Then clearly the task Ti will continue. Okay, it will continue to execute, and then it will acquire the resources and it will finish. Assume that it is going, but then what happens is that some task with a priority greater than Ti that acquires R2, then of course Ti will block on that task. But then again, as in the case of PIP, we have no reason to complain because that other task had a higher priority than Ti anyway. So we don't really bother. So as insofar as the inversion is concerned, we are only concerned about lower priority tasks. And given that the priority of Ti has already been raised to the value of ceiling of R1, its priority is already quite high. Hence, we don't have to bother for this particular case. So now let us consider the other case. So the second case, which is more important, is assume that R2 is currently acquired by another task Tj just before Ti acquires R1. So what is the relationship between the priority of Tj with respect to priority of Ti? And if they're the same priority, of course, we can use the FIFO logic. But let's assume that the priorities are different. So what we need to understand is that given that the priority of Tj is nothing but ceiling of R2, which is guaranteed to be greater than the priority of Ti, because Ti is also interested in R2. We have that the priority of Tj, which holds R2 just before Ti executes R1, its priority is greater than equal to the priority of Ti, right? So this is the important point is, if that is indeed the case, then Tj should be executing. There is no reason for Ti to be executing. Given the fact that Tj holds a resource, it is the one that actually should be executing at this point of time. And the fact that Ti is executing means that this is not the case. Means basically that R2 is currently not being held by any other task. Because if it was being held by some other task, then naturally its priority would be higher than Ti. And that task could be executing and not Ti. So we can have a similar contradiction for R3, R4, and Rk, which basically means that the moment Ti acquires R1, we can say that the rest of the resources are free. So which means Ti will not be blocked any further. It means that a high priority task in a task whose priority is much greater than the priority of Ti can later on acquire R2, let's say in the middle of this process. So this cannot be stopped. In a sense, Ti is over here, a very high priority task comes and takes over R2. That cannot be stopped. But the point is, then we have no reason to complain because the priority of that task was higher than Ti, and then we are not going to complain. We'll only complain if there is an inversion. So, given the fact that we have this all powerful statement, we can proceed further. So, there will be two corollaries. So, first is that in HLP, before a task is granted a resource, all the resources required by it must be free, right? And once it gets it, you will know that they are free, subject to the conditions that we have discussed. The corollary to the second corollary, I'm sorry, I go back, is that given the fact that these resources are free, you cannot possibly undergo chain blocking because the resources are free, right? So basically, you will never get blocked by a lower priority task, and that's why chain blocking is not possible. Chain blocking or unbounded priority inversion and so on is not possible, and this is an advantage. So we can extend this argument further, and we can also say, given that a high priority task will not wait for a low priority task, a cyclic loop will not form, so there will be no deadlocks as well. So something quite similar can be said using this relationship, where this is the all powerful theorem, right? So I cannot stress this theorem anymore, the importance of this theorem. So then again, we have discussed unbounded priority inversion, we have discussed deadlocks. That here also, given the fact that after acquiring a resource, a high priority task will never wait for a low priority task, we cannot have a deadlock, because you see, a deadlock has a cyclic dependency, right? So in the cyclic dependency, the priorities will increase, but ultimately for the cycle to complete, a high priority task has to wait for a low priority task, which this particular property, the one that we saw in the last slide, is preventing. And of course, unbounded priority inversion comes along with it. So all our enemies, unbounded priority inversion, deadlocks, and chain blocking, they are all gone, right? They are all kind of destroyed and by the highest locker protocol. But the point is, we are still not happy. The reason we are not happy is because we feel that the ceiling operation is unrealistically jacks up the priority of a task. So this is our main this is our main quip, right, with inheritance blocking of HLP, that it is raised to a very high value, and this unnecessarily penalizes intermediate priority tasks. So inheritance inversion, we have seen this example before, and where we will have, let's say, two tasks, and these two tasks, ideally speaking, have a higher priority than T1, but just because its priority has been bumped to the highest priority here, lower the number, higher the priority, these two tasks get a raw deal. This is inheritance blocking. So again, the calculation for the blocking time is quite similar. So we have seen this expression before, where CSKS is the critical section time for task K and resource S, right? This is the task, this is the resource. Use S is a set of tasks that may possibly use S. So instead of using, let's call it may possibly use S. So the maximal blocking time B for task I is as follows. So basically we look at this expression. It is the maximum of, so it is maximum across across the set of CSKS, which is basically across the set of all possible tasks while using semaphore S. So while using the resource S, this is the maximum blocking time across all possible tasks where both I and K, so both task I and both task K actually use the resource, and the priority of K is less than the priority of I. So here again the idea is that if I want to acquire a resource, any thread wants to acquire a resource for the first time, at that point of time it can undergo a priority inversion. In the sense, it is possible that at that point of time a lower priority thread is holding on to a resource. If I find the maximum execution time across all those lower priority threads, which is quite similar, same expression that we used in PIP, that will be the blocking time, because after acquiring the first resource in HLP the task will not block anymore, right? So basically that is why we have a single max here and we don't have the summation. So you can see one great advantage here, that we just have a single term. Because we had the summation in PIP, that was essentially taking us to chain blocking, right? So the summation was pretty much exemplifying and representing chain blocking, which in this case it is not doing. We just block only once and then our road is clear. So usage of HLP priority locking is supported in the POSIX thread API, but Linux doesn't support it. The old ADA programming language used to support, but again that is too obsolete now. The real-time specification for Java supports HLP. It's known as priority ceiling emulation, which is a subclass of the class called monitor control. So our main problem is this problem of inheritance related priority inversion. That is why HLP is rarely used in real applications, because intermediate priority tasks might start missing their deadlines. That is why we will take a look at the priority ceiling protocol in the next lecture. And the PCP protocol, the priority ceiling protocol, is a protocol that is used. All right. So this finishes this lecture. In the next lecture, we will discuss the priority ceiling protocol.